Good morning, good afternoon, or good evening. Welcome to this presentation on the upsampling filter for video applications. It is a standard. It's not full standard yet because it is being published for community comment. And this presentation is a help for those who are interested in the standard and may want to make comments. And predictably, the standard will be approved on the 20th of August at the next General Assembly. Next slide, please. So who is this organization EMPI? Well, it is an organization that has been founded almost 5 years ago. It's called EMPI, the acronym, Moving Picture, Audio, and Data Coding by Artificial Intelligence. We are international. We are based in Geneva, unaffiliated, and non-profit. We we promote the efficient use of data. And how can you promote that? By developing technical specifications that address an important issue that is called technical specifications for coding of any type of data. And in particular, we are interested in, but not exclusively, in data that are processed with artificial intelligence technologies and the technology that facilitate integration of data coding and the decoding components in information and communication technology system. It means that we develop the component, but then the component must typically be placed in a bigger system, and that part is also something that is covered by us. And we also do that because many are developing specification, but we have the looming problem of patents, and which is, of course, the right reward for people who have invested and have made innovation. But when they are combined with the standard, they may create issues, and we are here not to solve the issue, but to help the users of our standards. We operate based on an open international collaboration. If you are interested in coding, using data coding, using artificial intelligence, you are welcome to join if you support then our mission and the means to accomplish the mission. Can we go to the next? So in this 5 years, we have done something. And if you, maybe you can click on, so we have the first one, which is AI framework. We have on audio. We have one on connected autonomous vehicles. One on predicting the performance of a company. We have on gaming, online gaming, governance of the entire ecosystem, communication between humans and machines. But you know, it's the one where the machine understands what the human is saying, same for multimodal conversation. EMPI Metaverse model is one of our flagship standards. Neural network traceability is how do you measure the performance of traceability technologies added to a neural network. Same for watermarking. Object and scene, these are basic components for a lot of applications. Portable avatar is a format that we have especially defined. Profiles, because sometimes you need a subset of the standard. Qualifiers, I mean, it's a very important element, but it would take too much time. So this was the situation until a couple of weeks ago, but now we have the latest standard, which is video upsampling filter. And here is where I pass the baton to my colleague Alessandro, who is the one who has led the development of this standard.
Thank you very much, Leonardo, for the introduction. So I will introduce the framework where the upsampling filter is working and this will be implemented. Then I will introduce a little bit what super resolution is. It means, okay, introducing also some drawbacks of existing techniques, and then I will start to present the design procedure, the low complexity step that we follow to develop the standard, and provide finally some quality comparison results. So an upsampling filter for video coding is used in order to reduce in a way the complexity, the computational complexity on encoder on video encoding. So we start with a frame from a sequence, we downsample it in a lower resolution frames, we encode it, we transport, then we decode it, and then we apply an upsampler in order to reconstruct the original frame of the original resolution of the frame, with the hope that the quality that we obtain is comparable with the original frame that we had as an input. So what super resolution is? So we start from a lower resolution image that has lower detail, lower information, less quality, and we want to augment the information in this input image to improve the final quality of the image. That will be more will please more the end user that will observe this image. So as an example, if we have an image constituted by 4 pixels and we want to increase by 3 the resolution of this image, we need to have as output an image constituted by 16 pixels, of which 12 are unknown. Like you can see on the right side of this slide, the red pixel are the unknown ones. So based on the knowledge that we have of the 4 pixels that have been provided as an input, we need to reconstruct the missing information in order to provide a better visual quality of the image. So several techniques have been used in the past: filtering techniques, interpolation techniques, that is also a kind of filtering if we see in a general framework, but they provide good results, but not optimal result, where often we have pixelation artifact, like we can see in the nearest neighbor case, or aliasing artifact along edges. Or we have, if we employ bilinear BQP interpolation, we can have a blurring artifact or loss of details. So deep learning has been introduced in the last 15-20 years and has been providing great results in several types of applications. And one of these is super resolution. If we compare the results of deep learning approaches with the bicubic, traditional bicubic interpolation, you can see in this zoom area of the ground truth image in the patch, we can see that the blurring of the bicubic interpolation completely disappears, and the results of the deep learning techniques is fully comparable with the ground truth. Now, I will start with the introduction of the description of the standard. I will start with the filter requirement and then proceed with the design and so on. So, the requirement: we want a standard that a technology solution integrated in the standard that is able to perform 2 types of upsampling transformation, starting from standard definition to high definition, and from high definition to ultra high definition, or 4K. So in general, the requirements that were requested in the call for technology are the following. So we need to support different type of bit sample, 8 and 10 bit per component. The technology should be agnostic to the decoding system. We have tried on several encoding technology, should support color space, the traditional color space of video encoding application, YCBCR with 420 subsampling, different type of encoding setting, like random access, low delay at different QP, and we should support, as I showed before, 2 type of upsampling transformation, but in the future even not by 2, also by 4. And we need to provide a solution that is enough of low complexity in order to be used in real time in real world applications. So I will start with the design procedure that it can be divided into components, the data preparation, and then the training. Data preparation. So the data set has been prepared using encoding video sequences, where we need to provide a pair of images, the input lower resolution and the output higher resolution frames. And then what we have done, we have decomposed the images in patches in order to reduce the memory managed complexity during the training. We have built a training set where we have a data set where we have 80% of this data are used for the training and 20% for the validation. So we have the training, how it happened. So we have started with a pre-training, okay, of the neural network on a very large data set that is not related to video encoding. Once we have pre-training, we have this initial pre-training of the network. We wanted to fine-tune the network to the specific application. So using the data set that I have explained before, okay, we have encoded several sequences with different encoder. We have prepared the data set for training and validation, and we have fine-tuning the pre-training network. What means fine-tuning? It means that we need to froze part of the network to keep the learning components of the pre-training step, and we just train the unfrozen part of the network. So it's much faster, okay, than the pre-training step. However, since we use a lot of frame, a lot of images, and we have very high resolution imaging when we have the case of from HD to 4K, we need to reduce the complexity of the memory management of the GPU. And for this reason, as I said, we have decomposed the images in patches. So network design. Network design, it has been done in 2 steps to reduce the complexity of the technology that is being integrated in the standard. The first step, try to reduce the complexity of an existing baseline deep learning technology, and it's based on just the analysis of the structural analysis of this technology. So based on the structural analysis of this technology, we just try to answer the complexity, justify the results, the quality that we can obtain. So we reach a conclusion that most of the time the complexity doesn't justify the quality. We can have lower complexity and have pretty much similar results. So we start from a baseline that is called dense and residual Laplacian network. As you can see, the network is quite complex. So the backbone of this network is what is called a residual block. Okay, we have 6 residual blocks. Each residual block has a component called density residual Laplacian module, where in total 20, because we have 3 components, these 3 modules in each residual blocks, and in the first 4 residual blocks. In the last 2 residual blocks, we have 4 of this module. Each of these modules is constituted by a simple component that is called residual unit, and we have 3 elements for each DRLM, so in total 60. And then we have a lower level component that are hidden layers, 2 per each residual unit, so in total 120, and 64 feature maps. So how we can, starting from that neural network or deep learning technology, we have reduced the complexity. So we have identified 5 components: residual block, DRLM, residual unit, hidden layer, and feature maps. So very simple process, a bit is a bit time demanding. Is we can freeze one component. We can freeze 4 components and unfreeze one and change this component and see what are the quality result we obtain. When we are satisfied with that, we proceed with the other elements of the structure of the network, and we provide our change. So doing this kind of experiment, we identify that when we reduce drastically the structural complexity of the network, like in the model M8, where we reduced the network to 2 residual blocks, 12 DRLM, and 1 hidden layer and 32 feature maps, we can keep pretty much similar result in terms of PSNR score, but we improve in terms of runtime and memory management. So the distilled model is the following. So starting from 6 residual blocks, we have reduced it to 2 residual blocks. We have 6 DRLM per residual block, so we have reduced to 12 instead of 60. So we have reduced to 36 residual units instead of whatever we had before, and we have reduced to 36 hidden layer and 32 feature maps. So, but this was not enough in terms of computational performance. So we wanted to further reduce the complexity while retain similar quality performance. So we applied what is called pruning. So the general concept. So we can start from the reduced complexity networks, okay? And we want to remove components there, input output components, but we need also to take care about the dependency of this component within the network. So we need to see which, if we remove an input, how this input is connected to the output, and try to remove the interconnection in order to maintain the structural similar match between the input output of different layers. Okay, why we want to keep as much as possible the original quality performances. So what we have done is that we have started to using a deep graph algorithm to understand the dependency between the different layers of the network, and we have modified this kind of algorithm in order to use a kind of layer that I will introduce later. The original algorithm is not able to use it. So how it works, this grouping step. So we want to create groups of the component of the neural networks that are depending from each other. And this is all, when I know it, it will help me to understand. And when I remove one component, I know to what is depending, and I will remove the whole dependency. So as I maintain the structural matching between input and output of the different layers of the network. So in this example, I mean, the black line identify the dependency from the different input and output of the different layers of this example networks. And the deep graph, it takes into account the dependency to group the different elements of the network in groups where the layers are depending from each other. So once we have these groups, we need to identify the different type of layer and how we can prune these different type of layers. So one layer is the classical fully connected, okay? That is also presented in the neural network that we have initially reduced the complexity. So we can have the input and the output in the fully connected. If I remove an input, as you can see on the left of the slide, okay, that is identified with the red cross, I need also to remove the connection with the output channel and the relative weights. In the same way, if I want to move an output, as you can see on the right side of the slide, I need to remove the interconnection with its input and the corresponding weights. So another layer, the CNN layer, okay, that is also a part of the reduce complexity of the original network. So in this case, what I have. So if I want to remove an input, as is depicted in this slide, identified with the red cross, I will need also to remove the filtering result of that input. So I will remove, if the input that I remove is the last of the 3 input channel, I will remove the results of the filter to that input channel. That will be the results of the convolutional filter, the Tor channel in the forced convolutional filter, up to the Tor channel of the N convolutional filter. If I want to remove an output, since the output is reconstructed based on the result of the convolutional filter, of the N convolutional filter, if I remove the output N, I have to remove the results also of the N convolutional filter. A bit more complicated is how to remove the input and output of an upsampling layer, okay, because it's constituted by 2 components, the sub-pixel convolution and the pixel shuffle. And DeepGraph was not able to work with this type of layer, so we have extended this algorithm to work with that. So if I remove an input, as is depicted in this image on the left, in this case is the green one with the red cross, okay, the subpixel, what it does, if I want to increase the resolution by 2, I need to increase the number of channels, the size of the input image by 2 in its width and its height. So if I remove one component in the input, I have to remove the corresponding channel upsampling group that correspond to the channel in the input. At the same way, if I remove on the output that is on the right side, is again identified with the green, with the red cross, since that output is the result of the shuffling of the results of the channel upscaling group, okay, I need to remove the resulting of this channel upscaling group corresponding to that output. In this case, is the green one in the middle section of this slide. So this is briefly the introduction of the design of the standard. Now I'm going to introduce some performance results of this upsampling filter. So the test condition were classical standard condition. We have tested on different encoding technology. We used standard sequences that robot food market for Parker 3. We have supporting the same color space and subsampling as the requirement. The coding setting reflect the one of the requirement, the upsampling 2, and the bit sample 2. And we have evaluated, we're using different metrics, BD-RAID, BD-PSNR, and BD-VMAF. So I'm reporting here only the BD-RAID for now. So we have tested on different encoding setting, low delay random access, on different encoding, using 2 different types of transformation, SD to HD, HD to Ultra HD. So we have used one network for the overall QP. So as we have reduced the complexity usage of the standard to a real case usage. As you can see, the transformation from SD to HD is drastically improved the existing BD encoding technology. The results are compared to the bicubic interpolation, that is a standard upsampling filter using video technology. So we are improving from 12.2 to 22.5 in terms of bit rate. We have less improvement in terms of quality when we move from HD to ultra high definition, but it makes sense because we start from a much better high quality image. Okay, but we keep an improvement on all different encoding setting and on all different encoding technology. Then what we said, okay, why do we need to use two different networks for two different upsampling transformation? The upsampling process is the same. Why we don't use a unique network? So based on that, we have used the network developed for the case HD to ultra high definition to be used for the case HD to HD. And this is the last row. As you can see, we keep very high improvement in quality performances respect to the B-cube interpolation on existing video technology. We just reduce a bit respect to the case of using the developed network for the case of SD to HD to the case of SD to HD from 0.6 bit rate to 2.6 bit rate in the case of EVC used in random access. But in general, we have provided a quite good improvement of quality performances respect to the standard B-cube interpolation. So this is my presentation. Now is Leonardo, I leave you to you the button for the presentation of the last slide. Okay, Leonardo.
Sorry, I was muted. Thank you, Alessandro.
Right.
So there is one word, of course, that I must add to what Alessandro said, and that is that this is a standard, in the sense that in order to develop the standard, we had to explore different configuration and so on, and we have put together two procedures that you can use, one simply for the design of the filter, and the second one for making the filter simpler without significant loss of performance. Of course, this means that that you can design your own filter for your own application. That is my message. And now, if you can move on, what I said at the beginning is that the standard is not final. It's not final because in our procedure, before finally approving a standard, we expose a draft standard to comments by the community. The standard, the URL of the standard is here. You go to empire.community/standard, there's empire-evc/UFV, and you get version 1.0 here, and you can access the text of the standard, so that you can comment. You are invited to send your comment to the Secretariat. The deadline is the 18th of August, because, as I said, we intended to publish the final version by the 20th, unless we receive many significant comments. That in that case we may take more than a month. It will be on the 30th of September when we'll finally approve the standard. So with that, I think that we can close the recording.